In Chapter 12, this is our last day in Chapter 12. We'll be starting Chapter 13 on Wednesday. Kind of a quick review from our last time we met. We were looking at the equations here for getting properties of surfaces. The equations we have available for use, one is for the emissivity, absorptivity, reflectivity, transmissivity. So these are all in your notes. We're going to use those today to work a couple problems, starting off with this example. This is problem 1258 from the heat transfer text. And again, if you look at the other text, the heat and mass transfer, it'll be a different number end of chapter, but the same problem is there, just renumbered in the different text version of the textbook. This is what we're given. It says that we're given, I'll put up here, a diffuse opaque surface. And we're given a graph of that surface, its spectral absorptivity as a function of wavelength. Spectral absorptivity as a function of wavelength. We approximate it by this shape. The surface is kept at 1250 K, absolute temperature. We're asked to find, well, also we're given a graph of the spectral irradiation, G lambda, as a function of wavelength lambda. We're asked to find the absorptivity and the emissive power of the surface. Okay, so we start off. Okay, we're supposed to find alpha, absorptivity. We go to our available equations. There it is right there. Okay, write it down. Alpha equal, just like over there. Here it is. Now, we break it down and integrate by parts. Every time something happens at a certain wavelength, we integrate in that interval. So when does something happen? At 2, at 5, and at 10. 2, 5, and 10. So we first integrate 0 to 2. From 0 to 2, alpha lambda is a constant, 0.4. Pull 0.4 outside the integral sign. Integral 0 to 2, g lambda d lambda. From 2 to 5, 2 to 5, alpha is a constant. Alpha lambda is a constant, 0.8. Pull 0.8 outside the integral sign. Integral 2 to 5, g lambda d lambda. We'll put the other two in there just to carry it through completely. Next break point, 10. From 5 to 10, do the same thing. Next break point, 10 to infinity. And by the way, that arrow in the textbook is a big, fat, pink arrow. It means, when you read that, assume that g lambda is 0 all the way out to infinity. There's a big, fat, pink arrow in the textbook in this graph. That big, fat, pink arrow reminds me, alpha lambda is 0 all the way out to infinity. Okay, so 10 to infinity, Now, from 5 to 10, g lambda is not 0, but alpha lambda is 0, so that integral part goes out. From 10 to infinity, g lambda is 0, alpha lambda is 0, so 0 times 0, 0. Divided by that. Now, equal 4/10. This is the area under the g lambda lambda graph from 0 to 2. Here it is. Okay. G lambda, wrong graph, this one. There's the area, right triangle, 1/2 base times height, 4/10 times 1/2 base 2 times height 5,000. Second interval, 2 to 5. 8/10 times the area under the G-graph, 2 to 5. 2 to 5. That's that piece. Rectangle, 3 times 5,000. 3 times 5,000. Divided by the area under the G-graph from 0 to infinity. 0 to infinity. Okay, there it is. What is it? The right triangle plus a big rectangle. Right triangle, 1/2 base times height. Big rectangle, 10 minus 2 times 5,000, there. That's the denominator, okay? That's 45,000. I'll just kind of dash it in here. The calculation's up there too. Okay. Do the math. Alpha comes out to be 0.311. Okay, I've got the first thing, alpha, 0.311. Now I want to find E. We need epsilon now. Okay, here it is. Here's your library of possible equations. Ah, right there. There it is. Epsilon equal integral 0 to infinity epsilon lambda, that's spectral emissivity, EB lambda, D lambda, divided by 0 to infinity EB lambda, D lambda. So I need epsilon lambda to do this calculation. I don't have epsilon lambda. I was given alpha lambda, but of course, here's the magic word. Problem said the surface is diffuse opaque. Okay, diffuse, we know what that means. Kirchhoff's law. Spectral emissivity equals spectral absorptivity. So if I've given a graph of alpha lambda, it's also a graph of epsilon lambda. So this is a graph of epsilon lambda, or if you want, a graph of alpha lambda. Okay, so do what it says. Break this down into integrals 0 to 2 epsilon lambda EB lambda D lambda plus 2 to 5 divided by integral 0 to infinity between 0 and 2. Epsilon lambda is constant, 0.4. From 2 to 5, that is 0.8. Plus 2 zero terms, because alpha lambda, or epsilon lambda, is 0 from 5 to 10. Epsilon lambda is 0 from 10 to infinity. This would be, oops, here. 2 more zero terms. I won't put them in there, though. That guy we've already defined. The fraction of energy between 0 and 2 microns. F, 0/2, plus 8/10 This guy, fraction from 2 to 5. Okay, I've got to use table 12.1. So I go to my table 12.1, and I say lambda 1T. Lambda 1 is my 2 micron point. Temperature of the surface given, 1250. 2500. F 0 to 2 comes out to be, from the table, 162. Lambda 2T, that's 10 microns, 1250. 5, not 10. That's my 5 micron point there, 5. 6250. From table 12.1, F 0 to 5, 757. So, put those numbers in the equation. Epsilon equal 0.4 times a fraction, 0 to 2, plus 0.8 times the fraction from 2 to 5. The fraction 2 to 5 is the fraction from 2, it's actually our 1. Our 1, let's see where I got it down here. Epsilon, 0.54, did I get 0.54? Yeah, okay. Yeah, 0.757 minus 0.162, 0.162. Fraction from 0 to 5 minus fraction 2 to 5 is the fraction from 5, 0 to 5, 0 to 2. You get that guy. Subtract. If you do that, epsilon comes out to be 0.540. I don't want epsilon, I want emissive power of the surface, capital E. So then, emissive power of the surface is equal to epsilon EB, which is equal to epsilon sigma T surface to the 4th, which is surface temperature given 1250, absolute. Go ahead and figure it out. 74,750 watts per square meter. That's the emissive power of the surface. Now, notice one thing, that epsilon is not equal to alpha. But notice epsilon lambda equal alpha lambda because of the word diffuse. But epsilon is not equal to lambda because we didn't see the magic word gray surface. Epsilon is equal to lambda if we see the word gray surface. If the problem says diffuse surface, then this is true, but not that. 0.311, 0.540, no, they're not equal. So just a little reminder about Kirchhoff's laws relating emissivity to absorptivity. Okay, we've got both things now. But I'm going to carry it further. So let's put down what we've got here so far. We've got epsilon, okay. We've got alpha, okay. We've got tau. He told me, opaque surface, tau is 0. Got it. One more property, rho. We know rho. Alpha plus rho plus tau equal 1. Tau equals 0. That means rho is equal to 1 minus alpha. 1 minus 311. 689. Got it. I have all four properties now. Okay. Did I get capital E? Yes, I did. Got it. Capital E, I know. I found it right here. 74, 750. Did I find capital G? Yeah, I did. It's right here. What's left? Oh, there's a capital J. Radiosity. Okay, my capital J is E plus rho G. I've got E, it's right here. I've got G, it's right there. I got rho, it's right up here. I got everything. J is 105, 750. Anything left? Yeah, one thing left. Q net double prime. The net heat flux leaving a surface. The net heat flux leaving a surface, which is J minus G. I've got J. I've got G. 60,750. So even though the problem only asked for two things, alpha and epsilon, I had to find this guy to get this guy. So the checks are what he asked for that problem, end of chapter 12. But I've found everything you could possibly be being asked for. I've found the reflectivity, the transmissivity, the emissive power, the irradiation, the radiosity, and the net heat flux leaving the surface. So everything is done in this problem now for you. Okay, any questions on that before I go on to the next problem? Okay, example. This is problem 1259 in the heat transfer text. Okay, now, this problem, I'll read it to you first. The spectral emissivity of an opaque diffuse surface is shown below. Okay. So it's an opaque diffuse surface. At 1,000 K. And here's what he gives us. So that's the spectral emissivity graph. The surface is at 1,000 Kelvin. It's diffuse, it's opaque. Let me read the problem here again. Part A, find epsilon. Part B, find alpha. Okay, epsilon, alpha. Okay, notice there's no graph given for the spectral irradiation. No G lambda versus lambda graph. We'll need, I'll tell you what he's going to give us in just a minute, but for right now we don't have that. Okay, let's find epsilon. There's the equation, top equation. Epsilon equal integral 0 infinity divided by integral 0 to 6 plus integral 6 to infinity. Integral 0 to infinity. I'm not going to pull it down. We just did one. Here it is right here, middle panel of the blackboard. We just did one. I'm not going to do another one, okay? Break it down, integrate by parts, pull out epsilon lambda, 0.4, 0.8, pull it out, go to table 12.1, get the fractions, put them in there, get epsilon. So I'm going to say, using same method, as problem 1258. Get epsilon equal 0.611, I think. No, 669. 669. All right, so that's not a problem. Same thing. I'm going to save this middle part because I want to compare these two problems. So I'm going to go on and finish this problem over here. This was part A. This will be part B. To find alpha. Okay. We know the magic word diffuse. We know what that means. Alpha equal epsilon. We did it over there. Alpha equal epsilon. In this case, the author gave us a graph of alpha lambda. In that case, he gave us a graph of epsilon lambda. But for both problems, he said diffuse surface. So this is also a graph of alpha lambda. Okay. There's my equation right there, alpha. Okay. Here it is here too, alpha. Alpha equal integral 0 to infinity alpha lambda g lambda d lambda. 0 to infinity g lambda d lambda. Okay, look for breakpoints. There's only one, 6. Okay. Integral 0 to 6 alpha lambda g lambda d lambda plus integral 6 to infinity alpha lambda g lambda d lambda. Okay, let's do what it says now. Between 0 and 6, is alpha a constant? Yeah, it is. 8/10. Integral 0 to infinity, 0 to 6, g lambda, d lambda. 0 to infinity plus between 6 and infinity, yeah, alpha lambda is constant, 0.3. Got it. It looks very similar to the previous problem we worked over here. There it is. 4/10 times this, 8/10 times this, divided by that. It looks identical so far. Now comes the change. Was I given a G-graph? No. Okay, can't do that. But I'll read what he says now. What's the absorptivity of the surface when irradiated by a large surroundings of emissivity 8/10 and temperature 1500? Surface is irradiated by large surroundings at a temperature 1500 and 8/10 emissivity, 1500 Kelvin. Okay, now we go back to early chapter 12, and I drew a picture on the board. It's a picture of a large enclosure, and it had a small object in the large enclosure, and we said, it'll be in your notes, a little picture like that. We said if the room walls are at T surroundings, and this is a large enclosure with a small object in it, the irradiation from the walls of that large enclosure to that small object, the irradiation, what comes in from the walls, looks like it came from the spectral distribution, looks like it came from a black body at the temperature of the surroundings. So the incoming radiation, the irradiation, appears to have come from a black body at the temperature of the surroundings. Okay. So wherever I see a G in these equations, I can replace it with the EB lambda. So this is 8/10. Okay. And then I say, well, you know what that looks like? That looks like the fraction of energy from 0 to 6. Right. And I say, you know what that looks like? That's the fraction of energy from 6 to infinity. Right. Then what do? I go to table 12.1. Lambda T. Lambda, 6 microns. Temperature. Okay, there's two temperatures. There's a surface temperature, and there's the walls of the large enclosure temperatures. This tells me go to the temperature of the large walls or the surroundings, 1500. My fraction of energy, let's see what my fraction of energy is, 0.890. So, Take that, put that in the equation. Alpha is equal to 8/10 times a fraction, 0 to 6, plus 3/10 times a fraction from 6 to infinity. That's the fraction from 0 to infinity minus 6 to infinity. So I have, there it is, 1 minus 0.890. So that gives me alpha 0.745. Note, alpha is not equal to epsilon. Epsilon 0.669, alpha 0.745. Why not? Because the problem didn't say gray surface. The problem said diffuse surface. Diffuse surface, alpha lambda equal epsilon lambda, but not alpha equal epsilon. So, 2 problems on the board this morning. You got problems 2 for homework. One involves that technique, one involves this technique. All right, the difference. Here's what they give the same, the commonality. They both give a graph of a property versus wavelength. This one gave alpha lambda versus lambda. This one gave epsilon lambda versus lambda. This one gave the incoming radiation with a graph. This one gave the incoming radiation with a temperature of the surroundings. So that's the difference of the two. At 8/10, never appears anywhere in the problem, okay? If you read the words with this picture in textbook, it says, irregardless of the emissivity of the walls, that's what happens. I don't care if the emissivity walls is 8/10 or 1/10. It didn't affect the problem. That was put in there, but you never use it. You got to be careful. You can imagine some people in a rush on an exam will jump at that and say, oh, he asked me for the emissivity? Yeah, he gave it to me. It's 0.8. No, I didn't give it to you. No. It's never used in the problem. Just so you know that and be aware of it and don't make that mistake, on homework or an exam. Could you be asked for other things in this problem? Oh, of course you could. What's the transmissivity? It's set opaque, 0. What's the reflectivity? Do this. What's capital E? Fine. Multiply epsilon times EB. You've got it. Here's epsilon times EB. Done. G from there. J, net heat flux leaving the surface. So yeah, you could be asked for other things. This problem only asks you for 2, but you could be asked for more. Okay, just so you know what would be fair game to ask you. Okay, now, yeah. Mm-hmm.
Would a pure white and a pure black surface also be considered gray?
What does gray mean again? Do you remember? I'll tell you. Not a function of yeah. So there's a graph in the book for white paint. I'll tell you that, and you can look at it. Over certain regions, maybe it could be. Well, I'll do it this way. Let's take this one. The real graph might look something like this. We approximate it by a nice straight line, horizontal line, okay? First of all, that's the real white paint, for instance. Some color, whatever it is. Does it appear to be gray from 0 to 6? Yeah, it's constant. Is it gray over all wavelengths? No, it's not. So that's what happens, okay? You do it over a certain interval, you might be able to say it's gray over that region. Okay, now let's look at, go ahead. Yeah.
Why can we use that graph for alpha and then also for
Oh, okay, here's a good point here too. This one here now?
Yeah.
It was given like that, right? Now, your question's what again?
Why can we use it for both of those?
Because you see the magic word diffuse. There. Mm-hmm. I'll tell you something else. You can do You can do a rho lambda, because what is rho lambda? I guess I've already erased, oh, there, yeah. 1 minus alpha. So 1 minus 8/10 is 2/10. 1 minus 4/10 is 6/10. There's a rho lambda graph. So make an issue to say, find rho. Okay. Here it is. There it is. Sure, yeah.
Didn't you switch for 0 to 2, you did 1 minus
Oh,
8/10.
okay. Yeah, what was it, 8/10? Yeah, it was,
It was 4/10, then 8/10.
yeah, it's 1 minus, yeah.
Okay.
I don't want, for the next class, I'll mess this up here, okay. Okay, and so let's see what I had there, so I get this back to where it was. Okay, so we're 4/10 and 8/10. Okay, there. Okay, yeah, so it's 1 minus 4/10, 6/10, 1 minus 8/10, 2/10. Yeah, thanks. Okay, now, one last thing. When you're reading chapter 12, you might come across, and you will if you're reading it, a term called the intensity of radiation. It's capital I, the intensity of radiation. It's a term, for instance, that talks about radiation leaving the surface, and it brings in angles. It's directional. We're not going to get that involved with chapter 12. If you want, you could spend weeks in chapter 12. There's so many little things in there, but we don't need intensity for what we're doing. So if you do read chapter 12, if you see I, capital I, read on, don't stop. We're not going to talk about intensity. So we will not use this. You can ignore anything that has to do with intensity. Now, let's talk about surface properties. There can be directional, depends on angles, and hemispherical. Over all angles. Mean integrate over all possible angles. Then you've got spectral. Depends on wavelength. And then you've got total. Over all wavelengths. Integrate over all wavelengths. We did that right here. Integrate over all wavelengths, 0 to infinity. Okay. That means total. Now you can take any surface property, and now you play the word game. Pick one word out of column 1, one word out of column 2, and apply it to any one of the 4 properties. So I'm going to write it down now for hemispherical total emissivity. Total. Okay, now I'm going to write it down for hemispherical spectral emissivity. Now I'm going to write it down for directional spectral emissivity. If you don't like the word emissivity, make it absorptivity. Alpha is a hemispherical total absorptivity. Alpha lambda is the hemispherical spectral absorptivity. You can apply those qualifiers to any of these four properties. The textbook does this double subscript quite often in that chapter 12. We're never going to consider things that vary with angle, theta or phi. So anytime you see anything with a theta or phi in it, ignore it. Don't look at it. Intensity, no, ignore it. So all we've done in this class so far is we have two things. Like let's take alpha. We have alpha lambda and we have alpha. Okay, what are they? Alpha is the hemispherical total absorptivity. Alpha lambda, what is it? The hemispherical spectral absorptivity. Normally, we don't keep repeating hemispherical. That means integrate over all angles, theta. We don't normally say it. So when I speak about it in class, as I've done, if I say find the spectral if I say the graph gives you spectral emissivity, that's epsilon lambda. If it asks you to find emissivity, what do I mean when I say find emissivity? I erased it, but over here. Okay, here. What do I mean when I say find absorptivity? What I mean is find the hemispherical total absorptivity. So that's what the words mean. So in this case, with no subscripts, it means hemispherical total. With the subscript lambda, it means depends on wavelength. With a theta comma lambda, it means depends on direction and on wavelength. But we're not going to consider stuff like that. But just so you know again, so when you're reading chapter 12, you don't say, what does he mean by that? Yes, sir.
So we're just assuming that the intensity doesn't vary with angle, is constant.
No, don't even speak about intensity. It does vary with angle.
But not intensity, I mean,
Yeah, right, yeah. Alpha, all the properties here, we're saying are integrated hemispherically over all areas above it. Above, put a quarter on the table. The whole area above it, that's a total coming in or the total going out. Not a function of that angle there or this angle here, theta phi. Okay, just so you know the terminology in chapter 12 again, because it can be really confusing, obviously. Okay, now we're done for today, but I want to give you something here. So we have homework due today, just so you know. This is a bonus problem. This problem, maybe some people would like to pick up a point or so because of the first midterm. So this will help you hopefully. This problem counts for homework. You know, we have 10 problem sets, each one worth 1% of your course grade. So your total is 10% of your course grade is homework. This one counts one more point. So now I just add it to the homework. So you can actually get 11 points out of homework rather than 10. It might look like problem 3 of the last homework set. Yeah, it is. Because I had several people ask me questions about that problem. Okay, so here's again, in simpler terms. So solve that problem just like it says, and then that will count for one more additional homework set to kind of give you a chance to boost your grade, to make the difference in an 89.5 and a 90.5 A minus B plus, to make the difference in a 64.5 and a 65.5, you know what that means, okay? So a chance to get one more point on your homework. Okay, so that's it for today.